Now suppose that you toss a coin, okay? And the random variable y means the number of hands. So it can be 1 or 0. Then I use a capital letter. So this is a convention in the textbook, not my convention. So this is a capital letter, and this is a lowercase letter. So this capital letter means before I throw the coin. Okay? So this is before. This lowercase means after I throw the coin. And see what happens. Okay? So that timing makes a lot of difference. Before I throw it, I never know the outcome, right? So capital Y means a random value. We do not know what it is. Okay? But once I throw it and see the result, then I know the outcome exactly. So the smaller case is just a number, 1 or 0. Do you understand? So it's a random variable, and it's a fixed number. So this is just a general way to write down things like. So does it make sense? So what I'm saying is, what is the probability that this random variable y takes the value 0? Okay? Or we can write something like that. So that's the difference between capital letter and smaller case letter. So in this expression, we can say that the small y can be 0 or 1, but we don't want to say such a thing for the capital letter, right? Because it doesn't make sense. So that's the convention. Now another thing is, we ask a probability only before you throw something. Because once you throw it, then the probability is kind of obvious. It's either 0 or 1. It happened or not, right? So it's not a useful concept to do. So we always ask this probability before we do anything, where this capital letter is still a random value. Okay, so it's about the timing. Okay, so let me use this convention, the capital letter and smaller case letter, to explain this thing. So what do I mean by sampling distribution? So to explain this, let me show you a random draw, a random sampling with replacement. So I'm going to show you an example of this thing, random sampling with replacement. Just before I came here, I just made this thing. So in this box, there are small cups. Okay, and it has numbers. So this cup has 1. Can you see it? Okay, so we have 1, and it has 2. Do you see it? Now this cup has 3, right? And 4. So we have 4 cups. So I put it in the box. Now what's the meaning of random sampling? I mix them now. I have to mix them. And then I don't cheat. Okay? I don't see it before I draw. So this can be an example of a random sample. So what do we have? So we have 2. Okay? Now what's the meaning of with replacement? So I once draw this 2, I have to put it back. Okay, that's the meaning of with replacement. And then I draw again. And then I do the random sample. So it's very weird. We have another 2. But anyway, that's the meaning of random sampling with replacement. So let me introduce this notation, y1, y2, y3. We can keep going, okay? So what's the meaning of this y1? So this is the value of cup I'm going to draw in my first draw, okay? This is the value of the cup in my second draw. Then I do the random sampling with replacement. Now this is the value of the third cup that I'm going to draw, okay? So it's going to take some time, but let me do it, okay? It's very important to understand this concept. So suppose that I do the random draw of my cup. I'm in trouble. So what do we have? 4. And I put it back. So the outcome is 4. Now, do you understand if I say that this is a small y1? It's a realization, right? This is after I draw something. Okay, so this 4 is the realization of y1, means that the value I draw in my first happened to be 4, right? Now I do this again. 3. So y2 turns out to be 3. And then I put it back. Oh, it's not a random sample. So I shouldn't do it. Let me draw this. That's 1, right? So y3 turns out to be 1. So that's one realization of my sample. So this is one draw of these three random variables, right? Now, this is the random variables. This is the something I can think about before I draw anything. This is after I draw, right? So they are fixed numbers. So that's kind of clear. Now let me define another thing from this. So I'm going to say that y bar so it's an example of a sample mean, right? It has a capital letter, meaning that I'm going to think about this quantity before I draw anything. It's a random variable. Sum of 3 random variables, right? So it's a random variable. Random variable x and y makes another random variable x plus y. Same thing. Now, once I draw it, then this y bar has a value. So at this particular draw, it's going to be 1 over 3. And y1 happens to be 4. y2 happens to be 1. And y3 happens to be 3 and 1. So what is it? 8 over 3. So can I say that this y bar is a random variable and 8 over 3 is one realization? Right? So this is before I draw anything. This is after I draw. These 3 cups at random with replacement. So the thing is that, so this is a difficult part. So we say the sampling distribution, and sampling distribution happens when I draw the whole thing again. So I draw it once, right? So why not do the same thing another time, twice? So let me do it again. Again, this is my y1, the value of my cup, my first draw. What do you see? It's 3. Remember that. 3. We have 2. And 3, 2, and 4. So this is my second draw. I draw 3 for y1. See? 2. 2 for y2, 4 for y3. Now, once I have this draw, y bar may take a different value. So 3 plus 2 plus 4. So what do you have? 3. Now, the surprising thing is this. A visualization of a random variable y bar can be different. You just saw it, right? So y bar can take many different values. What if I do this 1,000 times? Then you're going to have 1,000 realizations, right? I have some, imagine that you're going to make a distribution, or what is it? I forgot the name of the. What is a plot like this? I just completely forgot. So out of those 1,000 visualizations, so you can make what is it? Just missed my mind. What? What's the name of plot like this? Histogram. So you just do this 1,000 times, then we can imagine that you can make even a histogram, right? So that's a sampling distribution of, in this particular example, of the sample mean. Now let me repeat. So we can do this random sampling with replacement many, many times, 1,000 times, 10,000 times, 1,000,000 times. And in each case, y bar may take a different value. Some values are repeated, but it's okay, high frequency. If you do that many times, then you can even think about the distribution of y bar. Something looks like this, okay? So that's the sampling distribution of y bar. And y bar has a distribution because it is a random value. Once you draw and observe the outcome, that it's a number, 3.4. But before you do that, it can be anything, right? So in that sense, it's a random value. So when we say distribution, again, that's before you draw anything. So everything is open as a possibility. Now, can we think about something like mean of y bar? Can you imagine things like that? So simply the center of this distribution. And can you imagine to think about the variance of y bar? Can you do that? It's just a variance of this distribution, right? So in that sense, it's actually not that mysterious thing. So that's why we sometimes say, let's calculate the mean of the mean. That's what it means. The mean, the center of the sample mean. There's something you can do. And we can sometimes say that we are going to calculate the standard deviation of the mean, or the variance of the mean. That's the second quantity, the variance of the sample. So that's something we are going to calculate. So let's try it together. Before I do that, let's review a few things. Do you remember this one, this notation, IID? Independently and identically distributed. Do you remember what it means? So the independence means the value of y1 does not affect the value of y2. And y2 does not affect the value of y3. So do you think that that's the case here? So I get 3. Does it affect the value for y2? No. Because we do a random sample with replacement. That's the meaning of independence. Now, identical distribution, what it means? It means that y1 and y2 have the same distribution. Can you see it? That's my claim. y1 and y2, even y3, they all have the same distribution. Because We do the sampling with replacement. We can even write down the exact distribution. So let me try it. So actually, the distribution of y1 looks like this. We can take 1, 2, 3, or 4 with equal probability. Right? y1 can be 3, for example, with probability a quarter, right? Same for other values. Now, what is the distribution of y2? I put everything back, right? So it's the same thing. So this distribution goes to y2 too. Same thing. Same for y3. That's the meaning of second I, this identical distribution. Does it make sense? Okay. Now we know that, so I give you an example up to y3, but why not just keep doing this? So you can think about a sample of y1 to yn for whatever value of n is. Okay? And then our focus is to find out the distribution of the sample mean. Okay, the mean of these draw. Now, what is it? This is day 4 reading guide, page number 3. There's an exercise 2. Can you read it at least? And then we'll discuss. So in this example, n, the sample size is equal to 2. So the sample mean is just sum of these two y's divided by 2, right? And we know that they're independent and they have the same distributions. The y1 and y2 have the same distributions, right? So it's natural to assume that the mean of y1 should be equal to mean of y2. That's the meaning of 1, meaning of having the same distribution, right? And let's say that that just happens to be mu. Mu can be anything, just unspecified number. Because they have the same distribution, the variance of y1 should be equal to variance of y2. I just use sigma squared for its value. Okay? So when we talk about mean and variance, we treat y1 as a random variable. Again, this is before I see anything. Okay? So everything is possible. So the question is, what is the mean of y bar and the variance of y bar? So let's think about this first. Now here, everything is a random variable. So we are going to apply one of the law we saw here. So that's the definition of y bar. And then can I say this? Now, which one I used when I go from here to here in this list? First one, right? So that's the law of expectation. When you have a constant, it just goes outside. And you can change the expected value and the addition. And, this expectation is equal to mu, again, mu. So the mean of the mean, the sample mean, is equal to mu, which is the mean of just one random variable, one draw. Okay? Now let's think about the variance. Now can you calculate this? You can use one of the law there, the law of the variance, and try this. Remember that those y's are IID. They're independent and they have the same distribution. So when you have the variance of two random variables, then you can separate it using the law of variance. Should we worry about the covariance? No, right? Why? They're independent. Now we have to take 1/2 outside, and you're going to have a quarter, right? So did you get this? 1/2 of sigma squared. Now what is the sigma squared? That's the variance of one row, right? You can calculate this variance because you know the distribution of y1. Again, let me just rewrite everything. So from this distribution, you can calculate sigma squared exactly in this example, right? The variance of your sample mean when n is equal to 2 is actually only a 50% of the variance of one single drop. Right? That's what it says. Now, does it make sense? Think about it. Keep that thought. Let's solve the third exercise. You see the pattern. Now n is equal to 3, and your sample mean is defined in this way. And the assumption is, it's not an assumption. So the mean is equal to mu. Because they have the same distribution, they should have the same mean. And they must have the same variance. So the question is, what is the mean of y bar? What is the variance of y bar? Did you get mu? What did you get? Over 3, right? Okay. So the important thing is, so we just changed the sample size. We just increased the sample size by 50%. Does it change the mean of the mean? It does not, right? So the center of the sampling distribution does not change. Just fixed at the mean of a single observation. But what happened to the variance? Now it was the half of the variance of one observation. Now when n becomes 3, it's only 1/3. It gets much smaller, right? The question is why? I think you know the answer. So as you increase the sample size n, the variance of the sample mean gets smaller and smaller and smaller. Eventually it disappears. It's like sample mean becomes a number. To be precise, it is very close to a fixed number because variance becomes smaller and smaller. Eventually it becomes so small that it's, for all practical purposes, it's equal to 0. So why it happens? So let me give you something more realistic. So let's say that y is your height. Okay? Individually, it has variation. Some are short, some are very tall. What happens if you take the sample mean? It has less variability, right? Why? Because they cancel out. In your sample, somebody that's short are cancelled by somebody who is quite tall. The sample mean only takes value which is much shorter in range. It has smaller variability. Does it make sense? That's the meaning of information aggregation. You have less uncertainty. So that's why we like to increase the sample size n. Okay, so these calculations are quite important for now and for later too. So a little bit later, we are going to talk about consistency. What does it mean? How to show, and efficiency, things like that, right? So for that calculations, these are very important. And I may ask something like this in the quiz. So be prepared for the quiz. Okay. Do you have any questions so far? No? So we are done. So that's 9 things you have to know about probability. And there's some additional topics here and there. And one is that I want you to remember the definition of the covariance and the definition of the correlation coefficient. Okay? So can you do that? So this is something we certainly did a lot in the statistics class. So just review these things. And there is an exercise 4. This is a good exercise. And if time allows, we may solve it together. Or if it doesn't, I may just give it as a problem set, as a part of problem set. So before we do that, this is one of the additional topics. I'd like to discuss something, some very mysterious things in the middle of page number 3. So let's read it together. So it says, actually the textbook says in page 32, there's a very kind of a mysterious statement. If the conditional mean of y does not depend on x. So what it says is, if the conditional mean of y given x, so this number, so conditional mean produce a number. Okay? This number can depend on the distribution of y, but if it does not depend on the value of x, so just to make it easy, just let's say that this number is a constant c. Okay? Now, a constant certainly does not depend on x. If this is the case, then the covariance between x and y always equal to 0. Okay? So that's what the textbook says on page 32. So we like to understand why this is the case. So it appears that the conditional mean says something about covariance, how they're related. So again, what this statement says is, if the conditional mean does not depend on this conditioning variable, again, it can depend on y but not on x, then x and y must be uncorrelated. That's what it says. Okay? So the conditional mean has, it says a lot of things. But one thing it says a lot is about the covariance structure. So this is the statement we like to understand. So why? So let's think about this together. Now let me make things easy. So my first method, I'm going to assume that c is equal to 0. Okay, just to make it easy. So one example of such constant is nothing. So if this is the case, the statement says, if the conditional mean of y given x is 0, one of constant, then x and y must be uncorrelated. So So y. Now, do you remember that the covariance do you remember this? So, to show that the covariance is equal to 0, we have to know what is the expected value of x times y, and what is expected value of x, and what is expected value of y. Then we are done, right? Now, as I said, actually yesterday, expected value of x plus y is quite easy to find out. But expected value of x times y is much harder, right? But now we know a trick. Do you remember that there's a trick that we often use to figure out things like that? The law of iterated expectation. So that's something we are going to use. Okay, let's calculate this thing first. E of x times y by the law of iterated expectation. So that's what the law says. Oh, I just switched the order. So let me not do that. I don't want to make you confused. So that's the law. Okay, so you have to memorize this. It's a random variable. Then what law says, you first condition on something. It can be x, it can be y. But in this example, condition on x makes sense because that's what the condition says. Okay? And then you take another expectation. So this is basically a weighted sum of these conditional expectations. And they should be equal. Now let's forget about this expectation, this outer expectation. Let's focus on this inner expectation first. Okay? Conditioned on x, meaning that you know the value of x. X is a constant. Right? If somebody says that x is 3.5, then you can treat it as a constant, right? Then can you take it out? So does it make sense to you? So inside of this outer expectation, we are allowed to assume that x is a constant because we assume that x is known, right? The constant can be pulled out of expectation. So that's why I pulled it out. Now let's think about this. What is the E of y given x? What is conditional mean of y given x? 0, right? C or 0 in this easier version, right? So this is going to be E of x times 0, which is 0. So this part is 0. Now let's think about E of y. Again, we have no idea what it is. So the only trick we know is the law of iterated expectation. Now, what is the E of y given x? That's 0. So we just show that this is 0 and this is 0. So the whole thing is 0, right? So at least if this conditional mean is 0, then we know that they're uncorrelated. Is it correct? So are you convinced? Now the second case, when C may not be equal to 0. So it can be anything, it can be 100. But still, as long as this C doesn't depend on x, they are uncorrelated. So why? So let's use this. Let's use the same strategy. E of x times y Why? By the law. Now, given x, x is a constant, I put it out. Now, what is this conditional mean? It is C. So we have E of C times X, which is C times E of X. Why? By the law. Now this conditional mean is C by assumption. So it's the mean of a constant. A constant. So covariance so the first term is C times E of X. And the second term is E of X times, what is E of Y? C. So that's here, okay? So we just proved this statement. So the thing is that it's kind of a surprising fact. So somehow if you know the conditional mean of two variables, like wages and education, what is the conditional mean of wages given people's education, like college graduates? If you can establish that this conditional mean does not depend on education, X, the conditioning variable, then you can always claim that wages and educations are uncorrelated. There's no systematic correlation between them. Okay, so this implies this. Usually it doesn't go the other way. Okay, so that's the relationship. So we may use it later. Okay, do you have any questions about this? Is it clear? Can I ask it in the quiz? I may, okay? So be prepared. So review it. Again, work together, study together. It's very important. So we are basically done. We still have enough time, so let's solve exercise 4 together. By the way, this is my plan. So we actually finished chapter 2, okay? So we can move on. But we'll move on to chapter 4, which is a regression. So after chapter 2, start to read chapter 4. Okay, I'm going to post the lecture notes tonight. So why don't you read exercise 4? So when you do that, remember the definition of the correlation coefficient. So let me give you an example. Suppose that X is the room temperature, which is pretty high, right? It's very hot. And Y is your body temperature, my body temperature. So what's the correlation? That's R, okay? Suppose that, so in our example that we did in the assignment, suppose that X and Y are measured in Fahrenheit, okay? So what is W and T? This is room temperature in Celsius. So how do you convert the Fahrenheit to Celsius? You kind of know the answer, right? Just a linear transformation. And this is your body temperature in Celsius. Okay? So what it says is the correlation coefficient between room temperature and body temperature in Celsius is still remains the same. So you can just remove this square term. Okay? If I remove the square term on both sides, basically it says that you can transform the variable, two variables, a linear transformation of two variables does not change the correlation coefficient. It's something we already know from the statistics. Right? So the correlation coefficient is in some sense unit free. You can use Fahrenheit, you can use Celsius. Or you can use kilogram, or you can use pound. Doesn't make sense. It does not change the correlation coefficient. The question is why? My second hint. So the definition of the correlation coefficient is the ratio of covariance divided by 2 standard deviation, square root of variance. Right? So your job is to calculate this covariance and 2 variances. How do you do that? Apply the law of variance and law of covariance. Okay, try it. So let me show you those laws. So again, this is very important. So which one is easier? So let me try this. Let's think about the covariance. So if you add a constant inside the covariance, does it change it? No. So we can ignore this constant, right? A and C can be safely ignored. What happened to B and D when you multiply a constant? You put it out, right? But remember, we don't change the sign. D is minus 1, we put out minus 1, right? So that's the difference between variance and covariance. So we have B times D covariance of X and Y. Is it right? Now, if you add a constant to variance, does it change anything? Does it change the variability? No. What about B? So we have to put it out, but you have to square it. Same for the second variance. Now, square root of B squared is B, square root of D squared is D, so they cancel out. It's covariance of X and Y divided by square root of variance of X times variance of Y, which is the definition of R. Okay? So again, when we show this and that, we only have a very few tricks. So the first trick is the law of iterated expectation. I know that it's hard initially, but have some exercises, practice, and just be used to it, okay? And the second trick is the law of variance, law of expectation, and law of covariance. So with these 2 tricks, you can solve almost everything.
If B is minus, square root of B square would not be minus. So
Okay, that's a good point. So let me be more exact. So so the point is, this is not exactly true. What I should have done is, so when you take this B and D out of the square root, you should have the right? So if D is minus 2, not 2, and if you square it, it's 4. But we don't just take out D, minus 2, outside the square root. We have to make it positive first, and then we put it out. So that's why we need this absolute value. So the answer is actually, so this is equal to R, and this can be 1 or minus 1. So we're going to say plus minus the correlation coefficient. So that's why the originally the question was not the correlation coefficient, but the correlation coefficient squared. So the original question says the squared correlation coefficient is equal to R squared, right? So that's why. Good question. Thank you. I forgot to mention. Do you have something else? Any other questions? No? Okay, so that's the end of this week. When you come back to next Tuesday, we are going to start the linear regression. So start to read chapter 4. And the quiz is up to today. up to everything we did at this point. Okay?